So fun.
Yeah.
How was the header in, blind spot on that last transition?
All right, so last we talked, we were looking at Turing machine programs. We got some examples of Turing machine programs. We looked at Turing machine instantaneous transitions, instantaneous descriptions, sorry, that model the transitions of a Turing machine over a particular instance of a program. So given that there's some kind of input on the input tape, we go through, we find that here is the path that the state machine takes. Every state that we're in, everything that is on the input tape, we learned how to describe this in instantaneous description form, and we fed this program that string. And it gave us these instantaneous descriptions that eventually led to termination and acceptance. So let's see if we can do something that we knew wasn't context-free. When we looked at the context-free pumping lemma, we found that A to the N, B to the N, C to the N was not context-free. So we showed that, but let's see if we can modify the Turing machine to now read C's in addition to A's and B's. So I'm gonna go back real quick to that program. This was the successful program for recognizing A to the N, B to the N. How could we modify this to represent A to the N, B to the N, C to the N? Yeah.
Rather than stopping on B and going back left, you can just keep going and map it to another C. You can all go on.
Yeah, what would we have to add here? What would be actual transitions that we would need to add B? Where would they show up?
Group 2, we kept instead of going back left, keep going right, and we then have Q4 as the final state, whereas Q3 is tracking and the mapping from C's is to A's and B's as well.
Yeah, yeah. So we wouldn't have to worry about something like if we ran out of A's while we were still parsing B's. We wouldn't have to worry about running out of B's while we're still parsing C's, but if we mapped all of the A's to B's, we would still need to go verify that there weren't any more C's to go read. But can we come up with the intuition for why we could see a Turing machine program being able to recognize that language? Intuitively makes sense? So this is evidence, at least, it's not a proof, but it's evidence that Turing machines are more powerful than either context-free languages or regular languages that can recognize more languages than that. We don't yet have a proof that it can recognize all regular languages or all context-free languages, but it can. And it can also recognize some languages that have not been recognizable by any language class or any machine or grammar type that we've seen so far in the class. Already stated this a good few times, but any algorithm we can write in any programming language, we can also write a Turing machine program for, which is really cool. Because we can write directly to the tape, instead of just being an acceptor, it can also be a transducer, which makes a lot of sense because our programs that we write in programming languages produce output, or can produce output. So we can use a Turing machine now to produce that same output. We just manipulate the input into the output, and now we have a transducer, not just something that can accept or reject a string, but something that can convert a string into something else. You could imagine that what you have is something defined to be a number followed by a special separator symbol, followed by another number, and then you could do binary arithmetic, where you would somehow replace the two numbers that were there and the separator with the answer to the sum of two binary numbers, or something like this. So this is exactly what an algorithm does. So we finally have a state machine that can fully map onto anything that we could otherwise do, which is awesome. So let's look at example 3. I already spoiled it. Given two positive integers x and y, design a Turing machine to compute x plus y. Luckily, this is This is going to be in decimal, so let's go ahead and, do I want decimal or do I want binary? Let's just do binary, I think that would be easiest. Now, let's even do unary. I think unary is even easier than binary. So we're going to be counting the number of ones. So if you see 1, 1, 1, 1, 1, 1, that would be 7. Representing the number 7. So the number of ones that are there, followed by some separator character. You can call that whatever you want. Maybe it's lowercase x, followed by some more ones. You just can't have a blank, because remember that a blank signifies the end of the input, and then everything following that will be blank. So you need what is going to be considered to be some kind of separator character. So if you had 1, 1, 1, x, 1, 1, then you would want the final result on the tape to just be 1, 1, 1, 1, 1 with blanks on either side. How could we do that?
You need a blank to separate your input and output, right?
You would be overriding your input. Whatever input wasn't used by the end of it would be replaced with blanks.
Oh, okay.
Yeah, you're going to be converting the input into the output. I forgot that I had used a single 0 on this slide. Let's still use the X. I think that makes a better separator character, because it's obviously not part of a number. If you have 0, then it just looks like a large binary string. So let's just say we have some 1s, followed by an X, followed by some more 1s. Let's see if we can write that Turing machine program. Take a little bit of time, work in small groups if you'd like to. Algorithmic ideas for this? How have you solved or tried to solve this as efficiently as you can? Or don't even worry about the efficiency. What is your thought process? Yeah.
So taking the idea from counting A's and B's, now we're trying to pair leading ones. Ones together is the big thing. In order to calculate the sum, since it's binary, the issue I'm running into is
Unary. It's gonna be easier with unary. If it's binary, then it's actually significantly harder.
So single one.
Yeah, single ones. So really, we're just counting the ones.
Like, you see a one at the start. Like, you could just, since it's just ones, it's like tally marks. Every one you could see, you could turn it into some other character. And then go all the way to the end and just put a one over there. And then go back, take a one, turn it into something else. Put it all the way at the other.
Okay, interesting, interesting. So we're gonna slowly move the first sequence of ones to the end of the second sequence of ones. If you turn it into, you probably wanna turn it into a blank, because then you would already be done with what's on the tape. By the time you hit that 0, just turn that into a blank and you're done.
Yeah,
What's left on the tape would be the bunch of ones. That would work. Does anyone have any other ideas for how they'd handle it?
So the goal is to take two strings of ones separated by the middle X.
Mhm.
You walk through the first group of ones until you see the X, you walk one more and you see a one here. You move back, change this middle digit into a one,
Mhm.
and then you move to the end of the list until you see a blank. You move back one, you turn that into a blank, and then you have just a.
Yeah. That's the smart way to do it. That's the really efficient way to do it. So we know that in unary, they're exactly as Lily said, like tally marks. So how many of them do we have when they're separated by that extra one? We really just need to put them together. Because that's all unary addition is taking some marks, some other marks and shoving them together. So we're gonna move right past the entire first number. We see that separator, we turn it into a one. Then we move all the way to the end until we see a blank. Backtrack, turn it into a blank. Done. And that will work no matter what. So it's actually quite few transitions. And again, this still has that example of a 0 rather than an X. But in this case, state Q0 is telling us we're moving past that first sequence of ones. So whenever we see a 1, we're just going to replace it with itself and move past that entire first sequence of ones. Eventually, we see our first 0, or the only 0. We turn that 0 into a 1, but now we move into a new state that says that we've seen that. So we're now looking to go past the second number until we get all the way to a blank. Once we see that blank, we're going to move to state Q2 and move back left. We're going to, seems a little wrong at this point, take on state Q2, turn a 1 into a 0 and move left. Why are we doing that? It just, instead of, it honestly would make more sense to make it a blank at that point and terminate. At least in my mind. Rather than going all the way back left, doing nothing until we get back to a blank. Is there some edge case? I can't think of an edge case that would actually represent, but in my mind, the solution ends when you recognize in Q2, you see that 1, you move to Q2, there, you take your last, it's even in Q1, when you see this blank, instead of writing a blank, you'd want to go back, turn this 1 into a blank, and then terminate.
There was a couple edge cases I could think of.
Yeah.
The first string was basically empty and there wasn't any ones, it was just, it started with.
Yeah, it starts with that.
Or if it has.
Yeah.
The second one.
But if we're in Q0, we can't see a blank, so we'd be moving past, the very first thing we'd see is, I get to this.
Yep, that's what I was trying to.
Yeah, so if it was blank, we would need some fork at that point to say we saw at least 1, 1, or we didn't.
Well, I was also thinking if you're reading ones and you get to the separator symbol and you read a blank directly after that, and you don't want to write a 1 here, you just want to turn that
Right.
into a blank.
Yeah.
You need more logic for that.
Yeah. So this would handle that. But those are the edge cases. Any questions on thinking about the solution? Even simple Turing machines for adding in unary turns out to be more complicated than you would think it would be. This is probably the most complicated question I could imagine throwing on an exam, and even then, it's probably too much. There is a lot of there's a lot of complexity in even simple Turing machine programs. But I think the most important outcome for all of you at this stage is being able to read them, know what they're doing, and being able to map what is possible and what is not. Because how many times in the rest of your life are you going to be writing Turing machine programs? Probably never again, but you might be asked to design or ask a question like, would it be possible to design a Turing machine program to do something? And then you would have to be able to answer yes or no because reasons. So I think that's the abstract, more important outcome. Questions on this example before we move on to some alternate Turing machine models? All right, we're gonna do it. So Turing's thesis states that this concept of a Turing machine, which he invented, is capable of doing any computation that any computer at any point is going to be able to do, which is really cool. But how would we actually be able to go prove that? How could we show that any algorithm we could write in a deterministic computer could be modeled by a deterministic Turing machine? What would that proof outline look like? That's kind of a scary concept to even try to tackle because it's so abstract, but the result of it is also so pronounced. You've seen that any time that you spend creating a program for a Turing machine is going to be difficult. It's likely that there are small errors even in simple Turing machine programs. Even as most of you are juniors and seniors in a computer science degree, you asked to add binary, something that is a relatively simple concept in some other class, asked you to write a Turing machine for that. Most of you would have Turing machines that have bugs in them. That's nothing against you, that's just the complexity of writing Turing machine programs. So how could we go try to map any algorithm to any Turing machine program? What would we do for that? And to do that, it turns out that it's way easier to handle this kind of logic if we now try to ask the question, how can we simplify a Turing machine and or make it able to handle more complexity with easier syntax? So we'll start by saying we know that Turing machines are more powerful than pushdown automata. But we need to now look at some different models of Turing machines. Let's start with equivalence of automata classes. We have shown and know that two automata are equivalent if there is a language that both of them accept. They accept exactly the same language. If we look at and zoom out, we can look at, okay, what are the classes of languages that each type of automata can accept? We found that DFAs and NFAs represented the same class of languages, regular languages. We found that deterministic pushdown automata could represent another class, but it was distinct from the non-deterministic pushdown automata. We know that in general, two classes, like the class of the DFA and the class of the NFA, are equivalent if for every possible abstract automaton in that first class, we can construct an automaton in the second class that also accepts that language. So for every NFA we could create, there is an equivalent DFA that accepts that same language. And we asserted that. We found an algorithm to convert an NFA to a DFA. And we didn't actually go prove it, but a proof does exist in the textbook if you're curious to go read it, such that we could go prove that these two classes are exactly the same. For any language that you could write an NFA for, you could write an equivalent DFA for. Of course, we also need to be able to say for any DFA that we could create, we must also be able to create an NFA, an associated NFA with it. in order to show that they're equivalent. Otherwise, you could do something like, if it was only one of these and not both of these, we could say, well, for every context-free language, I can create a DFA for it, therefore they're an equivalent language class. And that's not true. If we're looking at a Venn diagram of this, one of them is just inside of the other one. All regular languages are context-free, but not all context-free languages are regular. So we need both of these to be equivalent. This also applies to Turing machines in a way that if we're trying to show that there is an alternate model of a Turing machine, like the first one we're going to look at, a Turing machine with an extra tape. So instead of having one tape, there are two tapes, and the read-write head has positions in each one of those tapes and can move left and right in each one of those tapes at the same time. So you're reading two pieces of information for every transition that you're making. You'd have tuples or pairs of information. Is that an equivalent language class to a Turing machine with a single tape? So we're going to use exactly the same logic when I ask you about each one of these language classes. Are they equivalent? Think about, can we simulate this concept on a one-tape Turing machine? Can we simulate a one-tape Turing machine on a two-tape Turing machine? If the answer to both of those questions is yes, then they will accept the same class of languages. So the real way to do this, now that we have a Turing machine, is could we construct a Turing machine that simulates the other Turing machine? So we have a two-tape Turing machine and a one-tape Turing machine. Could you build a program in a two-tape Turing machine that simulates the logic of a one-tape Turing machine? Could you build a one-tape Turing machine that simulates the logic of a two-tape Turing machine? What would that construction look like? If we could construct both of these machines with the other type, then they would represent an equivalent language class. Does that concept make sense to people? You're just using Turing machines to construct other Turing machines. This is the same thing that we do when we emulate games. We're going to use a PC to emulate a PlayStation 2. Are they equivalent computational devices? If you could then on the PlayStation 2 go emulate a PC, then they would be capable of running the same kinds of programs. So that seems like a pretty straightforward conclusion based on all of this. If we know that the simulating Turing machine does exactly what the to-be simulated Turing machine does, then we can find a function between the moves of one Turing machine and the moves of another Turing machine. And that function allows us to state that, once we find it, that these are equivalent. Whatever this can do, there's an algorithm now to produce it on this machine. Whatever this machine can do, there's an algorithm to produce it on this machine. Therefore, they're equivalent. I lied, I said the first one was going to be a two-tape. We're going to do a stay option first. So we know that Turing machines can always move either left or right at the end of each transition. But what if we introduced a third option? We don't want to move left or right. We want to stay right where we are. Any thoughts on whether a Turing machine with a stay option is equivalent to a Turing machine that can only move left or right?
You could just do nothing and move right, and then do nothing and move left.
Yeah, yeah. So whatever it is that we did on the stay, do that same thing, move right, then do nothing and move left. Yeah. Did that make sense as to why that might be an equivalent class of machine? This is probably the easiest thing to show because you just do, you go right and do a no-op moving left, or move left and do a no-op moving right. So you can now simulate with two moves what the stay option is saying that you can do with one move. Yeah.
If you were to like write that out in the formal syntax, we're doing it like a do nothing, would you have to do it for every symbol in?
Yes. Yes, so it becomes notationally disgusting to try to say that if we're trying to read a single character, then in order to stay on that, we have to be able to look for every single character that we would find when we move right or left If it's an A, replace it with an A. If it's a B, replace it with a B. If it's a C, replace it with a C. If it's a 0, replace it with a 0, whatever the input, whatever the tape alphabet happens to be. For each symbol in the tape alphabet, for every symbol that you could possibly expect, replace that and move back left. And that seems like it would be really disgusting to do, but note that once you show that these two Turing machines are equivalent to each other, now you can just write stay. And you don't have to write all of those transitions trying to now make a program with a stay option. Once you show that it's equivalent, you don't have to go through the arduous labor.
Sounds a lot like CP instructions now.
Yeah. I think that it's really important to be able to show, honestly, because there are times, and computer scientists are very efficiency-oriented people, we don't like wasting time and effort and doing unnecessary work. So being able to show that we can now, this has to exist in one way, shape, or form, this is what the mapping looks like, and now you can construct Turing machines with a third option. Unlocks a whole new class of making it easier on yourself. Someone would have to go write that function, but once you do it once, now everyone in the world can write Turing machines with stay options, use that function, and now it can convert it to a Turing machine that doesn't support that. And maybe if the actual construction of a Turing machine would never support it, if that function exists, no one else who's writing Turing machine programs has to consider it. This is how programming languages are made. There's a lot going on underneath the hood, but we're going to abstract as much of that away from people. It all exists down in compilers, other things that you don't have to worry about while you are writing programs, and you just have to interface with the most basic form of the language to be able to produce complicated logic. So possible moves of a Turing machine now are left, right, and stay, because we have shown that they are equivalent. So if you ever want to write a Turing machine program now, if you just show that they are equivalent or state that we have shown they are equivalent, you may now include a stay option. Does it increase the power of a Turing machine? No, because it represents exactly the same class of languages. If you want to see the exact proof, more than just the intuitive, do a no-op and go back left, then see the text. We're going to ask more questions about other types of Turing machines. So multiple tracks, not just 2 tracks, but an arbitrary number of tracks. So now there's a read-write head. It's at a particular position, but it's the same position on each one of those tracks. Is this equivalent to a Turing machine with a single track? Thoughts?
You can put them next to each other on the same track.
The big question now is that, does it have, what's the diagonal proof of infinity where it is recursive infinity versus unbounded infinity? Because if multiple tracks is unbounded infinity, then yes, it's the exact same.
Well,
represented that
we
way.
do know that for any input, there's a finite amount of input. The tape extends forever. But the reason the tape extends forever is because we don't want to place a bound on the possible size of the input. In grad school, I was looking at a 66 gigabyte file of energy data. If we bound the tape such that it only can accept input of up to 50 gigabytes, that works for just about anything that you would need to do with a student. But for me, that program would have been impossible to write on a Turing machine, because the tape was not infinitely bounded. Maybe in the future, there's something where we want to place every single atom in the universe in a cell on an infinite Turing machine. There are about, what, 10 to the 88th atoms in the observable universe that we are aware of. If we had a Turing machine that was any less than 10 to the 88th, then we wouldn't be able to represent that. So the idea of a Turing machine is just abstractly, there is no problem that is too large, but for any particular problem, it's going to have a finite size.
Right, so I think that answers intuitively that if it's just purely unbounded and we're adding more unbounded onto it, it's still infinity, so.
Yeah. The way that I want to explain this is the concept between a one-dimensional and two-dimensional array. When we instantiate a two-dimensional array in one of our programming languages, how is it actually stored in memory? Yeah, there's memory is one-dimensional, right? There's a memory address, which means that it is in one dimension. So we make some kind of 2D array, and we just now take the first row, and that is here, we take the second row, and that is here, we take the third row, and that is here, and we're just now kind of splicing this and concatenating it. And we can use pretty simple math, where if we want to find out what is this, row 2, column 10, you would just say 2 times the length of a row plus 10. And that would get you to wherever this is on this system. And of course, you need to add to this the starting index of plus the. Sure, we'll call it that. So you just utilize that, and that gets you to this position when it's represented on a single dimension. Very similar with a multi-tape Turing machine, however long those inputs have to be, concatenate them together with a separator character on a single tape Turing machine, and now you know I'm going from one row to the next row with that separator character, and you are able to, now with some number of rules, figure out how to go left and right to be able to go down rows. To go down a row, you go right, however long the length of that row is, plus 1 for the separator character, or something like that. And you would be able to intuitively map a multi-tape Turing machine to a single tape Turing machine. Very similar logic to multi-dimensional arrays being represented in a single dimension, because that's how memory addressing works. So more powerful than a simple Turing machine? It's not. It is equivalent. We could go show that, prove that, but I think the intuition is enough for an undergrad level class. How about restricting the tape to be only unbounded in a single direction? So now instead of being unbounded in 2 directions, there is a cutoff, either on the left or on the right, and it's infinite in the other direction. Is that less powerful than a simple Turing machine?
Yes.
Yes, why?
Because we're taking away, the unbounded capabilities of the left.
Would that change, what's an example of a problem where you wouldn't be able to solve it with an unbounded single direction tape?
Take, for example, instead of just a set of positive or negative integers, you need both a signed and an unsigned integers.
That is a beautiful example, because it's exactly an example that I'm going to use later on to show that we can map the positive integers to all of the integers. So yeah,
When you alternate between the two, you can start at 0, 1, -1, 2, -2.
yeah, so you have some way of being able to map. You could represent all of the integers on this single tape, even though it starts at a particular place. And the integers are unbounded in both directions, but you start in this single dimension, 0, 1, -1, 2, -2, 3, -3. There exists no integer that you would not reach eventually.
Why wouldn't you be able to just take that integer, all those integers, and just shift it over to your infinite right direction?
Yeah.
No, it's.
The issue with that is, where do you start? What is the integer you start at?
You can't.
Because it's, yeah, it's infinite in the negative direction. There's no starting point. As long as you start somewhere in the middle, you can now move left, right, left, right, left, right, and you can reach an arbitrary endpoint at either of those destinations. Right positive or left negative.
But like in this, in this visible one right here, it just looks like that you can only just head left one time and then you can't go any further past.
Correct. But I will argue that any number of lefts can now be redirected into some number of rights.
Yes. That actually makes sense.
Yeah, so it's exactly the same as representing the positive integers and all of the integers. If you just now, instead of going from 1 to 2 to 3 to 4, if you want to add 1, you're going to move twice over instead of once. If you want to invert, then you move once over. Yeah, it's a very interesting idea of inverting, add 1. It still represents all of the numbers.
Right, can I just get a quick clarification? What is like, what do you mean by like restrict the tape so it's unbounded in one direction? Is it like if it goes in one direction?
Yeah, It's kind of like how memory works in a computer. There is a memory address 0. There's no memory address -1.
Okay.
And if you were to say now that I want an infinite amount of memory in my system, you could represent this in a couple of ways. You could either say it's now unbounded in both directions, where I can access memory address -10 million, or in a positive direction, where I could access address 10 million. Or I could start at 0 and just continue to go on forever. It's the same amount of memory, regardless of whether you make it infinite in one direction or infinite in 2 directions. And any problem that could be solved in one could be solved in the other.
So that's not less powerful.
It's not less powerful. It represents the same class of languages, the same class of algorithms, which is kind of a counterintuitive result, but the more you think about it, the more it starts to make sense. How about extra tapes and extra read-write heads? So now, in addition to this concept of extra tapes, the read-write heads don't necessarily have to line up with each other. If you say write, it's not saying every read-write head has to move right. Now each one can move independently of each other. Is that more powerful than a simple Turing machine?
A lot more movement.
Yeah, when you define what a move is, now you have to say for every single read-write head, left, right, left, left, right, 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 left, right. No, that's going to be a very long notational transition. But theoretically, is it more powerful or the same? It's probably not less powerful, right? That doesn't really make sense, but more powerful or the same?
Typically, I'd say the same.
Same.
There's always gonna be a way to have a state that says go all the way this way and then do something over there.
Mhm.
And then it's just a longer process to move between the read-write heads.
It might be a little bit more efficient to read 2 things at once and write to them, but that's an optimization problem, not a possibility problem.
Right.
It's pretty similar to having multiple tracks.
Yes.
You could just take the 2 tapes and concatenate them.
Yeah, and now you have 2 different heads that are in different places and they're still reading on the same tape.
Mhm.
And you could even do one up if I'll draw this out because it's. So if we have tape and a single read-write head that's at a single position on that. And what we really want is here. And what we really want is, I don't know, something that's also over here. In this tape, you would read this, do something, and then move right. And then you would ignore this and read that and do something, which is the equivalent to there's now one tape here and one read-write head here, one read-write head here. You could move this read-write head over here and now just read. So yes, it's more steps involved, but now you don't have to think about which read-write head am I trying to work with right now and move the whole system along with you. You really get a chance to divide up the system now into its components, and each one of those is now movable. So the answer to this is also no. Also the same class of languages.
Is that analogous to like forking or multithreading?
Yeah, that's exactly what can. Yeah, you have different forks that now are independently controllable rather than a single program that now has to work with tuples or triples or quadruples of data. How about adding an extra dimension to the Turing machine? So now instead of multiple tapes, now it's a grid of states, or a grid tape. So read-write head now, instead of moving left to right, can move left, right, up, down, and since we already said it's equivalent, or stay.
When you flatten the 2D array to 1D, you can also flatten the 3D array to 2D.
Is that extensible for an infinite number of dimensions?
Because you can use to represent one dimension higher in some other way, or even others with more tuples. So possible,
Yeah.
It just becomes more and more gross, and more dimensions to add on.
Yeah, absolutely. So it is this more powerful? It's not. It's exactly the same. So by understanding a simple single tape Turing machine, that makes it the easiest to explain as possible, but it's also the grossest in terms of writing programs, especially complex programs that have inherent multidimensionality. So this also explodes to, if 2 dimensions are not more powerful than 1-dimensional tape, then what can we do with a 3rd dimension or a 4th dimension or a 5th dimension? There's no limit to the dimensionality of the tape, and that does not change how, it doesn't change what is possible to be solved. It will change the efficiency of what's solved, but what is actually theoretically possible does not change. Questions so far on the modifications we can make to Turing machines and the fact that they're all equivalent in the end in terms of what's possible? So if I ever task you now with coming up with a Turing machine program for something, you can now use any subset of these to design a Turing machine program. You can now say, all right, I'm going to use an infinite 2-dimensional tape, because I can visualize that better, and I think that makes the problem simpler. Great, they're equivalent. No complaints from me. One thing we haven't talked about, non-determinism. How does non-determinism affect Turing machines? So far, nothing we've talked about has affected the computational power of the Turing machine. Any guesses about non-determinism? What would a non-deterministic Turing machine seem like? What would it do?
Instead of exactly left or right, you can now have something like the NFA, where you can say on this route, you can go this way, or you can go this way at the same time.
Yes.
Where now it's that analogy of, if I hit this intersection, I can split the 2 or more arbitrary cars and keep going.
Right. So what the equivalent of this would be is that whenever you reach a non-deterministic decision, you either fork the process, you're creating an additional Turing machine, and now saying, in parallel, one of these Turing machines is going to go left, one of these Turing machines is going to go right, and now we're going to both move on to the next instruction and continue to move from there. But now that we have 2 Turing machines, if one of those Turing machines accepts, then the whole system accepts. But there's no guarantee that there's only a single fork. The forks will grow exponentially. We just now need to have a system that allows us to have an arbitrary number of running Turing machines at the same time. When we fork a process, that's exactly what's happening.
Could you represent that as a bunch of tapes and rewrite heads in parallel?
Yeah.
Like
Yeah.
so that would not affect the computation power.
Just be
Huh.
So there's an element of parallel choice, but that parallel choice isn't particularly mechanical, because when you state something like it's an infinite Turing machine, we need to have the instructions in the state machine for how to handle that. Since there's no bound in that, and there are a finite number of states in the actual CPU of the Turing machine, if we had an infinite number of states, then we could allow for infinite parallelism. But because there's a finite number of states, that's what restricts us from being able to fork the program an arbitrary number of times. We have to provide an upper limit for that in the design of the Turing machine. So nothing about the definition changes in the Turing machine. All the transitions are now a function. Any thread that rejects or enters an infinite loop is irrelevant. Of course, how do we recognize that one of the Turing machines has entered an infinite loop? We'll get to that point, and yeah, this is why we can't write non-deterministic programs. Basically, if you now tying this whole concept of non-determinism together, why can't we write non-deterministic programs? And analyzing at a Turing machine level, you start to realize why it's not possible. You would have to have an infinitely large state machine in there capable of duplicating threads into an infinite number of tracks. You need to be able to create a track, create a read-write head, and work with that, which is exactly what happens when you fork a program. But now you can only control one of those at a time. Deterministically. Then eventually you go back and work with the other. So now it becomes kind of like functions and function calling, where there's one active function at a time, even though you might have 10 functions and have function pointers at different points in those functions, only one of them is actually executing at any particular point in time. The rest are paused, waiting for control to return to them. Non-determinism would be something like, we can handle that. One function isn't waiting for the response from another, it can continue parsing or continue working as long as it didn't need the answer from another process in order to continue working. You could work in that infinite parallelism.
That would be like if you had a hypothetical infinite array of CPUs. that
Yeah.
all working on the same problem.
Right, and none of them relied on each other, because otherwise you get a scheduling problem.
I know we're a little short on time, but would it be easier just to say if at least one machine terminates, then the whole thing can quit out? We don't need to worry about checking for infinite loops
Yes.
because we can't prove infinite.
What
loops.
happens if all of them are in infinite loops? Is one of them eventually going to terminate, yes or no?
Well, fix your program because that's the absolute answer. I'm sorry, because we cannot.
Well, there are some problems that cannot be defined as algorithms where we can accept yes or no, or we can decide yes or no. Sometimes yes is possible, but no, if the answer is no, then all threads will eventually enter an infinite loop. Then there is no fix to the program where you could ever be able to answer no. So we're actually going to study next week the kinds of problems that the answer to that is we can't know. You can't fix your program.
Don't use a Turing machine then, because it can't prove it.
Use non-determinism. Why haven't we just invented that?
Well, I don't know. My wife should be able to do this at this point.
Placing high expectations on your significant other, I like it. Placing impossible standards on your significant other, I appreciate
Checks
it.
non-deterministically all the time. It could run both ways.
You expect me to fork my processes and be able to go to the grocery store and go to school. Awesome, well, we'll stop here for the day, I think. We'll come back to this next week.
Engineers.
And we'll continue to ask what is possible, what isn't possible, and how do we know something isn't possible? How can we actually go show that? You're placing non-deterministic expectations on me, stop it.
Oh.
Have a great weekend.
Yeah.